Instead of concepts now, we are going to zero in more on the skills. This next topic, the reproducible work, is going to be the most skills-oriented, and it is going to be probably the more technical aspect of what you're going to see here today. In addition to talking about what reproducibility means and how we can make our work more reproducible, we'll also be going over a couple of tools. You already see Jupyter as well as Git here on my screen. And so we will be talking about those two tools. We'll be going through demonstrations that use these tools as well. But let's kick things off, because in order for our work to be reproducible, we don't start at the analytical phase. We don't start at the phase where we're already maybe writing some code or even collecting some data. We start before our study even begins. If you want to design a study that is reproducible, then you should absolutely consider either creating a registered report or a pre-registration. And you should also make sure that you have a detailed and citable methodology, especially for method-heavy fields like wet lab work. And then during your analysis, this is when you have your written out transactional steps, meaning if I take input data set A, here is the transformations that I apply to it in order to get out to maybe the statistics that I'm going to report in my paper. And then, of course, we want all of our digital objects under some sort of version control, because this gives you the transparent history as to how things changed over time. So let's begin at the top here. Before our study begins, I said we should consider making a registered report. What is a registered report? A registered report is a publishing format that emphasizes the importance of the research question and the quality of methodology by conducting a peer review prior to data collection. This, honestly, when I see registered reports, when I talk about registered reports, this is how I think science should have been done in the first place, especially with the peer review process. Oftentimes, the peer review process is going to be weighted by the actual results that you obtained. And specifically, if you're doing statistics, most of us are, they're going to be interested in, is P less than 0.05 or 0.001 or 0.01, whichever threshold is most befitting of your field. And they're going to say, did you get statistically significant results? And as much as we don't want that to bias the peer review process, it does. So what we should end up doing in our registered report process, you will start by developing an idea, just like you would with any regular study. You will then design that study. So you'll put together a methodology or a method plan here. And this is when we enter a stage 1 peer review. You're then going to reach out to participating journals for a registered report, and you're going to say, hey, I'm creating a registered report. Here's my study design. Here's my hypothesis. And what do you think of it? And then they're going to then eventually check you off and say, yes, this looks like a great study. We will publish this. So they're making that agreement to publish this at an early stage before you even collect data or write your report. You're then going to, of course, collect, analyze your data, and then write up the final PDF or the final article. And this is where you undergo a stage 2 of peer review. And the stage 2 peer review will be looking for things like, did you adhere to the original study design that you created? Or if you didn't, what was the reason you shifted and why? And this forces us to be transparent at every step. We can't just create a new hypothesis after everything's said and done and then say, I knew it was going to be this way the whole time. Instead, we are held true to our original study design, and we have to disclose any shifts, any changes in methodology that happened along the way because of external factors. And so that's what the peer review is going to look for. And then, of course, you will go and publish it. This is a fantastic publishing paradigm because it weighs the importance of good study design and a thoughtfully, thoroughly constituted experiment. And it weighs these over the importance of what were the results and were they interesting or not. Because you should be able to tell from the study design, regardless of the results that come out, you should know that based on just the design and the question being asked in the first place is this an interesting enough study for us to publish? And that is what a registered report is primarily looking for. Now, if you are looking for more information on registered reports, you can always go to the Center for Open Science website, or you can go to their Open Science Foundation subsidiary here, and you can find more information on registered reports, things like participating journals. But in the interest of time, I will just very quickly show you those participating journals, and then we'll talk about our next very similar semantically related topic of pre-registration. So here, I'll go ahead and click on this particular link. This is the Center for Open Science, kind of the parent organization around the Open Science Foundation here. And what you should know is that there's more information on registered reports here, but the thing that I find very interesting are the participating journals. There are over 300 journals who participate in the registered reports publishing format. You can either use a regular submission or, of course, a special issue. If you scroll down, you will see a list of all 300 of those particular journals. So what I would encourage you to do for your next publication, consider making a registered report. Of course, find out if there is a journal in your field to publish in that will carry or that will support a registered report, and strongly consider making your next publication one that is a registered report. Now, this is great if you are designing a study from scratch, if you are just starting fresh with a brand new study. We also have this idea of pre-registration. With pre-registration, which is different than a registered report, with pre-registration, you are still going to undergo the same exact, the standard publishing route that you always would have. You will not be undergoing peer review in advance. But with pre-registration, also coined as registration, in case it wasn't confusing enough, with pre-registration, you are simply specifying your research plan in advance of your study and submitting it to a registry. All this means is that if I come up with a question and I come up with a hypothesis, I should be able to write up my reasoning, my motivation for that question, which is the background, right, of my final results. I should be able to write that up. I should also be able to write up the expected methodology, the expected plan of analysis, and the expected direction that the hypothesis will fall. And what I'll do is I can write all of this up. I don't need to talk about the results. I can talk about theoretical results. I don't need to talk about the methodology. I can talk about what my plans for the methodology are. And I write all of this up, and then I submit it to an external service. The external service notes down me as an individual using usually some type of identifier like an ORCID or your first and last name or your first and family name. You will also submit, or it will also record the date and time that you submitted this pre-registration, so a timestamp here. And then, of course, all of the information that you defined and submitted. And this is very important because what we can do later on is you're going to say, hey, I have an idea to do X. Here is my idea to do X. I'm going to do it in exactly this fashion, pre-registration, published. Now you can take your time and go and carry out your study. If that's a year-long study, if it's a few months long, if it's a multi-year-long study, you can conduct that study. And then when everything is said and done, you go throughout the normal, just regular publishing paradigm of going to a journal, undergoing peer review based on your results and your paper, and then finally publication. And what you can do is you can allude to the fact that you were intending to publish this the entire time. In fact, what this will also help you do, it helps you be transparent because it helps you identify what your original plan of analysis and your original methodology were. And then you'll have to talk about how that has changed in your final publication. And I will say this even goes so far to help you prevent being scooped, because in order to be scooped, somebody has to be, quote, first to market or first to publish an idea. But even if you are second to publish on a specific idea, you can say, hey, I've been collecting this study for 2 years, or I'm working on this study for 2 years already. You can see my pre-registration. So based on being first to market, my pre-registration was there first. And so a pre-registration will help us combat all of these different things. It will help us combat this idea of p-hacking and data dredging. And if you're not familiar with these terms, what you can think is that most publishable studies are based or analyzed with some form of statistics, and there are ways that you can bend those statistics to help lower that p-value and help find, quote, significant findings. And so typically what's done with p-hacking is if I have two groups of individuals and I plan to compare these two groups of individuals, but the statistics don't come out the way I want them to, what I can do is I can take those two groups of individuals and I can split them arbitrarily into 4 groups, into 6 groups, into 8 groups. And then I can continuously analyze and beat these groups for information until I get my desired test statistic. And what ends up happening is I'll say, okay, we didn't see a difference for 2 groups, but we saw a statistically significant difference when we tested for 4 groups. Therefore, we're going to present as if we always thought there were going to be 4 groups. This is p-hacking. This is you're taking that p-value and you're trying to minimize it by arbitrarily reducing the power of your study. And if you have submitted a pre-registration, we will know that originally you were only planning to analyze 2 groups, but in your publication, there were 4 groups somehow. You'll have to address and explain that. And so pre-registration will help you combat p-hacking. And if this is a standard that you hold yourself to, then why not hold others to the same standard? It also helps us combat harking, which is an acronym for hypothesizing after the results are known. And I've alluded to this before, so I'll be quite brief in my explanation. Harking simply means that you think hypothesis A is going to be the coolest thing ever. You design a study to test hypothesis A, and it doesn't turn out the way you were thinking it was going to be. And so then you start p-hacking, you start beating the data until you get something statistically significant out, and you find out that when you split the groups from 2 to 4, well, now we get some good results. And well, I never thought I never thought we were going to need to go to 4 groups, but in my publication, why would I ever admit that? In my publication, what I'm going to say is that I studied hypothesis B, and I will never mention or allude to that hypothesis A was ever under consideration. And with pre-registration, what I have to do is I have to write down what my original hypothesis is. I have to say, I'm conducting this study to answer this particular question of hypothesis A. And then when we get to my actual publication, I am then held to my original expectations, and I'll have to admit, hypothesis A didn't work out the way that we thought it was going to be. However, upon further analysis of the data, whether this was a planned post hoc analysis or not, and of course you'll have to disclose that information, we found another interesting finding. And then it's, of course, up to you and your peer reviews to figure out, well, is this a valid hypothesis, or did you just kind of p-hack your way into coming up with a new hypothesis? And so this is what harking is. It also helps us reduce or combat publication bias, selective reporting, meaning filtering out your data or filtering out maybe subsets of your data to figure out what you actually will report on. It helps ensure we do not do these things. And these are probably the things that if you're a diligent researcher, you will look at and you'll say, I would never do that. And if you would never do that, I challenge you to put it in writing. Submit a pre-registration with your next study. And the very cool thing about pre-registrations is that since they changed the name from pre-registration to registrations, not to be confused with registered reports, the implication is that you can create a registration during your study design. You can do it during data collection. You do not need to do this before your study was initialized or created. You can do this at any step. And that is what the Center for Open Science encourages us to do. You can, of course, check out more information at their initiative/PeerReg link. It's fairly easy to get started. You simply fill out a web form. And that web form will ask you questions like, what's your hypothesis? What's your planned population of study? How are you going to study this? What's your methodology? And all the points that we have iterated before. And there's even a step-by-step guide to help you do just that. So know that you can do this before your next study. You can do this during data collection. You can do this after data collection. But of course, it just gets more and more merit, more and more weight the earlier in the study design that you do it, because then it gives us even more weight or more confidence that you are not doing any of these bullet points here: p-hacking, harking, introducing bias, or using selective reporting. So this is another way that you can also combat getting scooped. When you go about pre-registering, you will know it's helpful to know that there exist many services that will all give you those features, those core features that I talked about. It'll give you a timestamp, it will give you a searchable registry. It will maybe even provide anonymity if that's a good thing for you. But I will say that the Open Science Foundation is probably one of the best places to submit your pre-registration. Whether you use their templates or open format, I highly suggest their template format because that is the web form that you can simply walk through, fill out all of the boxes, add collaborators, and then click submit, publish, and you can even update it after the fact. Those updates and their previous versions will still be available. Using a service like GitHub, which we'll talk more about later, isn't really suitable because GitHub history or Git history can be synthesized, and so that's not going to be useful for us. Another service like As Predicted is going to be helpful, but you cannot search As Predicted. And also, I don't believe you can use As Predicted if you do not have an academic email address. That's an email address at a university or another academic institution. And so Open Science Foundation and even Zenodo are great, but of course, the Open Science Foundation has a great wealth of other tools. And so I'd encourage you to check them out in addition to their pre-registration and registered report tools. Now that we've talked about the steps that we can plan for reproducibility before our research even starts, let's talk about what we can do during our analysis. And the first thing I want to present to you all is a question. Why would we ever bother using programming or coding? You'll probably have noticed that in the last 2 decades or so, it's increasingly more difficult to do or conduct research without using some form of a programming language or some use of a scripting language, whether you're using formulas in Excel or whether you are using a full-blown programming language like Python or something else. And I'm curious, why would we bother doing this in the first place? Why can't, if I have just data on, say, 20 participants, why can't I use a pen and paper and then just enter results into a spreadsheet manually? Is there something so wrong with that? And so my question to you all in the chat, let me know your thoughts on why we use programming or coding in the first place. Is it really worth learning this skill? Does it really contribute to the reproducibility of our work? And so do take a moment to enter your thoughts into the chat. Of course, I do have my own thoughts as well to share with you all. All right, so let's get the ball rolling. I'll help us get the ball rolling here. Ooh, providing a framework to create simulations and making the work efficient. Technology can solve problems and tasks faster and more accurate, right? There's likely not going to be those small math errors where if I divide by, 2, I round incorrectly or things like that. Less user bias and errors. So I want to challenge some of these because there's going to be as much bias in a program or a script as the user has written it. These are human-made scripts. So there's still going to be some bias. Easier to search and retrace steps. I absolutely love that one. Standardization, some data protection. I can see a little bit of data protection there because it allows you to cleanly separate the storage of your data from the actual analysis of it. And a little bit of automation to make the work more automatically. And so that is actually my first idea. One of the biggest reasons that we would use programming and coding at all is it provides automation. And automation is a very important thing in science because it means that our actions are all performed in a uniform and a consistent manner. And this is a very specific form of automation because you can think, at least in my own experience, when I was working in undergraduates, I was part of a lab. And for this lab, it was another fMRI-based lab, and we had to analyze some fMRI data. And I will say that these videos of brain activity over time, the data sets are fairly large. For a single participant, we're talking about a couple of gigabytes usually. And so if you have 60 participants like we did, well, we're going to have probably 60 to 120 gigabytes of data. It's not huge, it's not massive, but it is large. And the thing about analyzing this data is that even for a computer, it takes a couple of hours to perform a couple of the computational steps required to analyze these data. And what we had in our lab was a tool that would open up a graphical user interface on your computer. You then had to select every option, every drop-down, input every text box, input every file manually by hand. And so in order to automate this task, the students or the graduate student overseeing this particular task, or I should say the postdoc overseeing this task, created a packet of papers probably about this thick. And this packet of papers had printouts of the graphical user interface. So it said, when you get to this step, make sure you select this dropdown, this checkbox, this widget. And you had to follow about 10 to 15 pages of all of these screenshots of the graphical user interface. Then they handed this packet out to not just myself, but to 4 other students. And we all independently went and analyzed or we pre-processed these data sets. And since we were all doing this independently, following the same printed out guide, well, now we know that there might be some room for mistakes. Did I interpret something about the instructions differently than one of my colleagues or peers? Checking that is actually quite difficult or tricky. Did I make a mistake one time? I'm a human, and so I might have forgotten to check the box that says do the extra analyses or conduct second level analyses. And I forgot to check that on one subject's worth of data. How do I go back and check that? There really is no way for me to go back and check that aside from looking at the output and saying, this output looks funny, right? And so with automation, if we had a computer or a script that could do all of these, well, we know that they would at least, even if there's a mistake, they are at least performed in a uniform and consistent manner. And that is what programming or coding gives us. It gives us automation with all actions being performed uniform and consistently. It also gives us reproducibility. Others can run your work from the original inputs. And so if I have a script and I have some data that goes alongside of it, the idea is that all you need to do is run the script and everything should just work. And this is different than reproducibility, where if you say, hey, Cameron, can I have access to your code and your data? And I say, oh, there's no code, but here's the original data. And what I did when I analyzed the data, silly me, I calculated the mean, the standard deviation by hand. I then inputted those values into an ANOVA so that I then calculated the ANOVA by hand. And I used this lookup table to find the F-stat for this particular. And you're thinking, okay, I appreciate you writing all of these analytical details out in a bullet pointed email for me, but I'm never going to do this. And so although the work is theoretically reproducible, in the real world, it's not going to be reproducible because it's too time consuming. Programmer coding, you just say you run this and you should get the same results I got. If you didn't, that's a concern for reproducibility. We should talk about this. We should figure out how to make this more reproducible. It also gives us preservation. Now, somebody mentioned this in the chat. Preservation means that you have a written record of transformation and collection. Now, you can probably think, well, you also have preservation in the publication, right? The publication should outline the actual analytical plan that you used. And at the end of the day, those are not the actual executed steps of transformation and data collection. Those are words that describe the actual steps that were carried out. But with code or programming, you have line by line, the computer is doing exactly what is written here. The computer is doing exactly what's written here. And so I don't need to have access to your publication. I can simply read through your code and say, oh, okay, I see you calculated the mean here, you calculated the standard deviation here, you then got your F statistic from your ANOVA distribution here, or your F distribution here. And so this is what we mean by preservation. It is a line-by-line record of what was actually done and carried out, not a description of what was done and carried out. It is the actual record. Quality. Code can be reviewed and improved by others, as was pointed out in the chat as well. It can be forked, it can be improved or adapted for new studies. Collaboration. Code serves as a common language. And I say this now in my life when I do a little bit of programming, consulting work, especially with academics, even though I am not a subject matter expert in the field of, we'll say, physics. I can still read code that physicists have produced to analyze their data, and I can provide feedback on that code. I could even be listed as a collaborator because of the volume of contribution I made to other people's code. And so, although you might not have a specialty within a particular field or a completely different field, you can still use code as a common language. I can still tell you, if you join your two data sets in this fashion, you're going to end up with a lot of faulty data. And so this might impact your down the line findings. And then finally, scalability. Programming coding typically will give us access to computational methods that can handle huge data sets and very complex models. And these are things that traditionally are graphical user interfaces or are, I will say, corporate tools are typically going to be a little bit behind the curve on. So this is why we use programming coding. We have automation, reproducibility, preservation, quality, collaboration, and scalability. I'm very impressed in the chat. You actually got most of these already without even us having to go over them. So excellent, excellent job. Now, let's talk about some common tools for data analysis. We have two sets of tools that I'm going to disambiguate. And the only reason I disambiguate these two sets of tools is because they are often conflated for one another. On one hand, we have programming languages. These are going to be the actual paradigm or the things that interpret the text that you write that then execute specific functionalities based on the text that you have written. So I can use Python to write code. I can use R to write code. I can write code in Matlab. These are languages. On the other hand, we have interfaces and development environments. These are typically going to be things that we will actually do the physical coding in. It's going to be that graphical user interface that pops up, and then you can write code in. Now, the thing that's confusing is that these entities, languages and IDEs or interfaces development environments, are usually tightly coupled, meaning if you use R, you probably first used R through RStudio as an interface. If you use MATLAB, you probably use MATLAB through the MATLAB IDE, where you can write your code in one place, and then you have access to like a variable explorer on the right. You have access to a built-in debugger on the left by the line numbers. You have access to the current working directory and all the files, so it's easy to see everything. These are interfaces and development environments. They are separate from the actual underlying language. And so this goes to say that you do not need an IDE to write code in any of these languages, but it does usually make your life a whole lot easier. And I want to take today to spend some time talking about one of the most popular analytical tools for many programming languages, and that is Jupyter Notebooks. Jupyter stands for Julia, Python, and R because it was originally designed to support those languages, but I will say it supports more languages than that now, so the name is a little bit out of date at this point. But Jupyter is a development tool that, or should say, Jupyter Notebooks and Jupyter Lab is a development tool that facilitates the rapid iteration of code. It binds code output directly to input and allows you to interleave code with plain text or markdown text. Now, if none of those bullet points meant anything to you, that is perfectly okay because we are about to step into a demonstration on Jupyter that I want you to follow along with. I will say Jupyter is not the only way to write or run Python code. Now, before we jump into our Jupyter demonstration, I did want to just very quickly revisit some of the benefits for coding, and that is coding or programming gives us increased capacity for automation, specifically a uniform and consistent form of automation, where if there is a mistake and the mistake exists within the code, I should be able to fix that mistake and then either click rerun or rerun the script from top to bottom, and it should regenerate new outputs for us. Programming coding also gives us access to increased or heightened reproducibility, and I will say simplified reproducibility. It also gives us a preservation, a written record of line-by-line transformation. It increases it gives us access to increased quality because code can be reviewed and improved by others. And in this same line, it gives us access to heightened collaboration. And finally, code will typically give us access to tools that allow us to scale our models or our methods to massively sized data sets. But let's talk about Jupyter. Now, if you have never used Jupyter before, what I want to do is this. I'm going to share a Google Colab link here. Now, I know Google Colab is a different tool than Jupyter is, but Google Colab has a very similar interface to Jupyter. Now, this is what the Google Colab link looks like. If you open that up, I've pasted it into the chat. It will allow you, if you sign into your Google account, and you can only use it if you're signed into a Google account. That's one of the shortcomings here. But I will say, if you are signed into your Google account, you will be able to run all of the text and all of the code inside of this notebook. And in this particular notebook, you'll see this is actually a piece that I have written about the central limit theorem. Fear not, we are not going to talk about the central limit theorem or anything to do with statistics. I simply wanted you to see some of the features that this notebook format has to offer. I can write text. I can write a table of contents using that text, and I can jump around the notebook very easily. And interleaved amongst that text is the actual code that's executed to generate these particular figures and the particular results here. And so instead of using Google Colab here, I want to show you actual Jupyter. I simply wanted to use Google Colab as a way where you could see a very similar interface and even get started with a tool today just to play around with it. I will also mention that if you are going to be using Jupyter, you need to know the underlying programming language. By default, Jupyter will support Python. You can have it support other languages like R using various installed kernels, but I will say there's going to be a couple of additional setup steps that you'll need in order to do that. Instead, what I will do here is I'm going to take us to my terminal window. I do a lot of work in my terminal window. It gives me access to a number of different tools, and specifically, one of those tools is going to be Jupyter. If working from the terminal is a brand new thing and this feels very daunting, I would highly encourage you to look for more graphical tools, something that you might be familiar with, and a great tool to get started with a lot of these different programming tools is going to be Anaconda Navigator. It's a great point and click way to get started with a programming language, to install tools like Jupyter Lab and access them from a point and click type of interface. So what I'm going to do is I'm going to start a Jupyter Lab server here. And when I do this, you'll note that it's going to put a lot of text on my screen. The text isn't that important, but it's also going to give me a couple of links here. Now, these links don't actually go to the internet. They will open up in a web browser. And so what I'll do is I'll go ahead and open up a web browser here, and then I will click on this link that we have, or I'll actually even copy and paste the localhost link here. Copy that, and I'll paste it into my browser here. Like I said, although I'm working within a web browser right now, this is not living online. Nobody else except for me on my computer can access this specific link. That's typically what our local host means. And so I'll full screen this because we're going to transition entirely into this interface here. And you'll see that I see a couple or all of the same files that I had previously. I have my .ipynb file. This is our IPython notebook. And if I open up this particular file, you can see it looks just like it did on Google Colab. And I should be able to run this thing from top to bottom. But instead of showing you a notebook that I have already created, I want to highlight many of the features that you will see in a Jupyter notebook. And what a better way to do that than just working from a brand new empty notebook. Here you can see I'm selecting the language that's being used by default. We do have Python 3 here, so I'll click select. This means that the code that I type is all going to be interpreted as Python code. So it lets me do things like print messages to the screen. I can type this text in. I can then come over here and click the play button to run this particular code. And you'll see that it generates the output for me. And then it brings me to a brand new code cell. Now, we're not just limited to printing things. I can do math. I can say, what's 2 plus 4? And then I can use a keyboard shortcut to execute that. You can very easily see, well, 2 plus 4 is 6. In our programming languages, although they support all of the same features you would find in a calculator, it's much fancier than that. If I want to assign variables, I can say x is equal to 4, y is equal to 2. What is x times y? and we get 8 because 4 times 2 is 8. The nice thing is that I can also use these variables that I've created across code cells, so I can always re-reference x, and I can ask, well, instead of multiplying, what is x to the yth power? In this case, what is x squared? In this case, I get 16 back out. And so we have some programming language basics here. But in my other notebook that you saw, not everything I was writing was simply code. Some of it was actually being rendered just as text. And so this gets us to two very core ideas of the notebook, or of any notebook. And that is the idea of cells. You can see as I click around inside of this notebook, there's going to be a blue rectangle around the currently active cell. And all this means is that this cell has a particular type. Right now up here, this dropdown under my mouse, you can see that this is currently a code cell. And so what I'll go ahead and do is I'll create a new cell at the very top here. And it's going to default to being a code cell. But what I want it to be is a markdown cell. A markdown cell lets me simply write text. And so I'll say this is text. And when I run that cell, if I use the play button here, all it does is it renders that text right onto the page. It doesn't execute it. It's not being executed as code. There's no math going on. There's no programming going on, really. And Markdown is a language that lets you embellish your text a little bit. And so what I'll do is if I prepend a single pound sign or a single hashtag to any given line, this makes this line the title of the document. So let's go ahead. I'm going to title this document. We'll say my first notebook here. And under this, what I want to then do is create a subtitle. My first subtitle, well, in this section, we've just shown some of the capabilities of our programming language. So I'll just say Python code here. And I can even include a description. This is a notebook, a demonstration notebook created to highlight some of the features that Jupyter has to offer. And when I render this now, you'll see that the line that I prepended with a single pound sign becomes very large. And the line that I had 2 pound signs in front of also becomes large, but not as large as the first level header. You can also see that I have the ability to now interleave code with markdown text. And so what I might do is say, this code simply prints out a message. And then I can come down here and I can say, let's show off some math. And I'll make sure that this is a code cell, and then I can render it. And now what I'll do typically with this workflow is I will write a description of what I believe is being carried out, and then I show you the code immediately underneath it and say, here is my actual evidence, or here is the actual thing that I did, that I described from above. But I will say that our programming languages we're still not even showing off the full force or the full features of our Jupyter Notebook here. And so what I will do now is I'm going to create a third level header. So there's kind of a subsection within a subsection. And this is going to be simple math and variables. And then now let's come down here to the very bottom of our notebook. We're going to make a new code cell or a new markdown cell. And we're going to say, we're going to create some figures and graphics. Because since we have the full strength of Python at our disposal here, I can go ahead and create a simple graphic. I can import matplotlib.pyplots as PLT, and I can create a very simple chart. Now, what you would typically do is you would load the data from some particular file that you have on disk. I don't have access to any data set right now. So what I'm going to do is I'm going to create some variables. I'll have some fruits. We'll say an apple, banana, and orange. And then we have some values, or we're going to have some counts. And so maybe this will be like the apples I've eaten, or the fruits I've eaten so far this week. We'll say that I have eaten, I actually don't like bananas. I've eaten 3 apples because apples are great. I've eaten 1 banana because I'm not really a big fan. And I've eaten, let's say 5 oranges because I have the small ones like the clementines or tangerines. They're not oranges, but bear with me. And I've created these variables. And the whole idea is I want to maybe create, let's say, a bar chart that highlights which of these fruits I've eaten and how many of them I've eaten. And so what I'll go ahead and do is I will create our figure and our axes. And understanding the actual code that's being written here is not horribly important. I'll decrease the figure size to, let's say, 4:3 here, because sometimes the chart that shows up is really massive and it scrolls off the screen. And what I can then do is simply set up a bar chart. I want a bar chart. I want my x-axis to be my fruits. I want my y-axis to be my counts. And, oops, small typo. It should be Matplotlib. And we will see our, oh, and this should be height, not y. So we have our x and our height here. And there you can see, here is my bar chart that shows apples, bananas, and oranges on the x-axis, and then the number scaled on the y-axis here. Now I can do other things, and the very nice thing about the Jupyter Notebook interface is it lets you, and if you remember back to one of the bullet points, it lets you rapidly iterate on code. So I can do things like ax.setTitle here. And this will let me add a title to my chart. So I can say, maybe make an informative title and say, I've eaten a lot of oranges this week. And there is my title. I can set my Y label and just say consumed, N consumed, or number of consumed, or number of eaten. And then, of course, our X label here. And this is, of course, I probably don't need this label at all because it's not, I think if you see apple, banana, and orange, most people will know that it is fruit. So maybe I decide to leave this off at the end of the day. But at the very least, you have a way to write some code, view some outputs, judge whether that output is what you're specifically wanting or looking for, and then decide, do I need to edit it? Because maybe I don't like the look of having a bar chart that's fully enclosed in these lines here. So maybe I'll do something like this. I'll take off these spines and we'll say, take off the top spine and take off the right spine here. And we'll just make them invisible. And then now you can see I don't have a line along the right-hand side of this chart or the top portion of this chart. I can further refine this, but I think we get the idea of what's going on. You have the capacity to write some code, view some output, and then revisit the code based on what the output looks like to you. So that is about it for the programming language features. I want to talk just very quickly about some Markdown features, and we'll wrap up this demonstration. Our Markdown features are plentiful. We have the capacity to write in different fonts or styles. I'll actually just say styles here, text styles. And what I mean by this is you've seen basic text so far, right? And it's not rendered fancily at all. Well, I can also write bold text. And if I want something to be bold, I simply surround that text in 2 asterisks. If I want italicized or italics, then I simply surround any particular text with single asterisks on either side. And when I go to render this, you see that I have my basic text, I have my bold text, and I have my italicized text here. So we'll just call this bold and italicized. Just like that. Now, we also have the capacity to perform some hyperlinking. Hyperlinking is very important because we'll often want to link to either external resources or even other places within our particular notebook. And the easiest way that we can do that is if I use, let's say, I'm just using google.com here. If I just paste https://google.com, well, you can see that automatically it's detected that this is a link, and now I can click on this. And when I click on this, it opens up in a new tab, and that is fantastic. But what happens if I want to embed this link? What happens if I want to say, this is a link, and then have the word link just take you to google.com? Well, we can do this with a combination of square brackets and parentheses. You put them side by side next to each other. In these square brackets, you want the text that's going to correspond to the link. And so what I'll say, this is a link to Google. And I want the phrase link to Google to be the actual link here. And then from there, all we do is we grab the hyperlink and we put in the parentheses. And when I render this, you will see that we have plain text here. This is a, and then we have the link to Google. And when I click on it, it takes me back to Google's homepage. Now, we also can embed images. This is a little bit trickier, but it can be very useful to do. You can embed images from your own computer or from the same repository, or in this case, let's look for a Jupyter logo on their Wikipedia page, because I want to grab the Jupyter logo and then embed it inside of this particular notebook here. And so here we have the Jupyter logo. This is probably going to render massively. So let's see if we can find one that's just a little bit smaller here. Maybe the Wikimedia Commons will have a smaller one, 207 by 240. Yeah, let's grab the smallest one. Oh, actually, there's a 44 by 51 pixels here. I love that. It's been saved as a .svg.png. That's very funny. All we do here is we grab the link that points to this particular image, and then you'll notice if I just try and embed it as a regular hyperlink, you'll see that this is some text. It's clickable. I can click on it. It takes me back to the page. But what I want is I want this image to be rendered within the inline notebook. So what I do is I put an exclamation mark before a set of empty square brackets, and then I put my parentheses with the link to the particular resource in question here. And when I do just this, you'll see that this logo is in fact rendered in line here. And in fact, this is just, it's a little bit small. So let's grab the larger one. I'm going to copy the link address. I'm going to come back here. I'm going to paste this in. And now we have a fully embedded link or fully embedded image. All right, so now let's talk about our next feature, and that is going to be our bullet points. For our bullet points, we can have numbered lists. Let's use some bold font here. Numbered lists, or also known as ordered lists. And to create a numbered or ordered list, pretty simple. You just put one dot and then say first. You can say this is our second bullet point. I can even indent this and put A now. So if I put A, this is going to be like a sub bullet point, so on and so forth. When I render this, we'll see that this all gets very nicely rendered out. You'll see that I can just start over my numbering system from one there, and we get our sub bullets. We can also have unordered lists or just your typical bullet points, standard bullets. We'll also call this an unordered list as well. To create an unordered list, you simply prepend any particular line with a hyphen. So this is our bullet points 1, bullet points 2, and then sub bullet point. And under this, we just get the very basic standard circles or squares with our bullets and our sub bullets here. So that's our bullet points. And then finally, last but not least, we have math jacks. Because what you've probably seen so far is we don't have a nice way of writing mathematical formulas. MathJax implements kind of a subset of LaTeX. And so if you are familiar with LaTeX, this is probably what you're going to be reaching for. If I want to do something like y, or write out a phrase like y is equal to 1/2 times x plus b, and then I render this, it doesn't look very good. This does not look like what you would see in a handwritten mathematical formula. And that makes it a little bit harder to read. And so what we often reach for is another language that lets us express math specifically. To do this, all I need to do is, just like I had bold and italicized fonts or styles, I can surround any line inside of dollar signs. Everything inside a set of dollar signs is going to be rendered by the MathJax renderer here. And so just by doing this, you'll see that I have an improved rendering already. We get the Greek lettering for our standard letters, and we even get a slightly italicized font, emphasizing the numbers and de-emphasizing the operators here. But we can clean this up a little bit more because I don't need to indicate the actual multiplication symbol. Typically with our handwritten formulas, we're going to leave no space next to our math and our operators here. But now we've introduced kind of an ambiguity. Is this 1/2 x or is this 1/2x? And so typically what we'll do here is instead of just putting these two numbers together, we'll present this as an actual inline fraction. And to do that, we take our fraction, we take a 1 and a 2 here, and now all of a sudden we have 1/2. We put the x next to it, and then we add plus b at the very end. And this gives us our linear equation, our linear formula. And this is our notebook. Let's go ahead and save this. This is going to be my first notebook, just like that. And we have successfully saved this notebook. If we open up the File Explorer here, you can see that we have this notebook here. It's been saved. And I can even go back, open up my table of contents, and I can see the beautiful headers and the beautiful tables or contents that we have made here. There are more features to Markdown than this, but I simply wanted to walk you through some simple Python code and some simple features that Markdown has to offer and how you can combine them into a very coherent and nicely organized analytical space. We're going to talk about version control and sharing. And I mentioned earlier that these two things are very tightly related to programming. Well, it turns out version control is not just related to programming, it is related to anytime you want to keep track of text documents. And so we'll get into what version control is first. So why do we use this? What is it and why do we use it? Well, version control is really the ability to collaboratively track and manage changes to files. If you have used a Google Doc before, you're probably familiar with this. If you've ever looked in the top right corner of a Google document, you'll see that it snapshots your work for you about every 10 or 15 minutes or so by default. And of course, you can change that. And you can, of course, take the manual snapshots as well and give them a title. So that is what version control is. And so let's imagine this particular scenario. We email our most recent draft of a paper we're working on to either an advisor or a collaborator. And when we email this draft, maybe we think they're not going to edit it too much. We're really close to publishing on this one. And so you have a beautiful title for your document that in the attachment that you send. It's a Microsoft Word document, and it's titled paper_final.docx. That's a very bold title to send if you're just giving this to your advisor or collaborator for your first time. But what ends up happening is that your advisor collaborators make edits to it, or they make suggestions for edits, and then they email it back to you. And when they email it back to you, they alter the name slightly. Instead of it being paper_final.docx, it's now paper_final_advisor_edits.docx. And this process then continues. You accept or reject, you go back and forth accepting or rejecting the comments or feedback, and then all of a sudden, after about 10 emails, your document is no longer titled paper_final.docx. It's titled paper_final_v2_Cameron's edits 4_advisors edits 5. I promise this is actually the final version of this document, .docx. And if you have ever been a part of this process, you'll know that it is such a headache because although you eventually get to something that you want to publish on, you have almost no ability to go back and say, what did the paper look like on January 4th of this year? What did the paper look like before my advisor made comments on this particular section? When did they change this particular section? And you will have a hard time trying to go back and find when those changes were made. You have to align things with dates of emails. Maybe you have to read the body of the email. Hopefully the body of the email described what was changed, but more often than not, it's going to be an email with a vague subject line, no body, and just an attachment. And so this is one of the worst scenarios to find ourselves in, because although we end up with something that we can submit as a PDF, well, you're not ever going to be able to make change or make use of all that history and how things evolved and changed over time. So instead, let's say we are now in the modern day and age, and if we're collaborating on some writing, emailing a document back and forth isn't the easiest way to do this. Thankfully, there are many more collaborative tools that exist today. We can use a Google Doc, and you share this with your advisor or collaborators. This allows you to simultaneously edit and collaborate on specific sections of documents, which is huge. And it even does version control for you. It snapshots the document every 10 or 15 minutes or so. So if you want to say, well, what did this look like on January 4th of this year? You can scroll back through the history. But what happens with a single Google Doc if you need to collaborate on multiple documents? Say you are collaborating, you just submitted something for publication, and you created the first version of this draft as a Google Doc. And one of the reviewers, usually reviewer number 2, let's be honest, will come to you, or not come to you, but they will write and say, oh, I like this, but you made one minor mistake in the analysis. You used a coefficient of 2 when it should be a coefficient of 3. And then now you're thinking, okay, well, that's not too hard to fix. I just need to go back to my analysis, change the coefficient from 2 to 3, rerun the analysis, and then go back and change the results section. And hopefully this doesn't impact my conclusions. And now we're concerned because now we need to make a change that ties these two documents together. We have to make a change to the code, the analytical code that we have, and we need to make a change to the paper. How do we tie these two things together if the paper lives in a Google Doc and the code lives maybe somewhere else? It's very hard to tie these two things together. And so Google Docs does not give us the ability to collaborate across multiple documents, all using the same form of version control. And also with Google Docs, what happens if your collaborator, your advisor uses the editing button instead of the suggesting button? And all of a sudden they are overwriting work that you had done without your heads up or without your approval or say so. So while this is a fine scenario, it's not really ideal. But imagine this scenario. You use a new tool, you share a GitHub repository with your advisor or collaborator, and you can collaborate on and edit specific sections across many documents. You can throw your paper into a GitHub repository and put it right next to your code. If your data sets are really small and text-based, usually, you can also put them in that GitHub repository as well. We have other strategies for versioning data sets because they often exist in a very different space than our text human-written documents. But you can have a GitHub repository with these files in it, and you can make changes to multiple documents. And then you can tie all those together with a nice message and nice metadata saying on January 4th, I got feedback from reviewer 2, I incorporated it, and I I made all of the changes to incorporate that feedback into my written code as well as into my written document. And so this is what version control gives us. This is what a tool like Git and in collaboration with GitHub will give us, the ability to collaborate across multiple documents. And I will say, by default, all edits are suggestions. And you have a nice space to go back and forth on edits, whether or not they should be incorporated fully or partially. And then once you're happy with what the edit looks like, you can then decide to go ahead and incorporate it in your paper. So this lets you very easily collaborate with multiple people. So let's talk about the specific tools now. We've mentioned Git and GitHub, but I haven't really disambiguated them. I haven't told you what the difference is. You can think of Git as a tool that is used for version control, similar to how that Google Doc version control, you can set it up so it takes snapshots. I wouldn't recommend that using Git though. And Git is a tool that operates not just on a one document, but on an entire folder and every document within that folder and every subfolder within that folder, so on and so forth. You can make, using Git, you can make checkpoints or snapshots of your whole repository. And in this case, repository is just another word for your whole folder that's under version control. And you can make those checkpoints or snapshots with associated metadata. And so this is very beneficial for us because we're not tied to a single document. This is a tool. Git is a tool that lives and installs on your local computer. You don't need to go to any special website to use Git. So with that said, GitHub, on the other hand, is an online service. It is a collection of user-made repositories. You can almost think of this like Google Drive, but instead of it being private by default, most repositories are public, meaning you can search through them. And so GitHub is searchable. It integrates really, really well with our local tool, the one we install on our computer, Git, hence the name GitHub. And it supports collaboration with both known as well as new collaborators. If you have a public-facing repository, anybody can come across your code, provide feedback, and provide changes to it. And so let's take a moment to talk about GitHub, because I am sure that many of us have used GitHub, or at the very least, even if we haven't used it ourselves, we have found a link to a GitHub repository, and then we get to it and we're thinking, what am I supposed to do with this? And so let's go ahead and explore the GitHub interface. I'm going to be using the link in the chat in order to explore the GitHub interface. It is a link to the Seaborn repository created by Michael Wascom, which is a Python package for statistical data visualization toolkit. And so I'll go ahead and jump us to the next slide because I want to highlight some very important things for us to look at while we are on that GitHub page. Specifically, we're going to be talking about the stars. We're going to talk about the date of last commit and what that means. We're going to talk about issues being opened and closed, pull requests being opened and closed, contributors, forks, and watches. These are all properties of a GitHub repository, and they are typically, if they are done well, you'll be able to tell, and it will give you your first sign that this is an actively worked on project. This is a project that many people use. These are things that give you confidence that this is a tool you can use because other people are using it, because they're actively working on it, so on and so forth. So let's go ahead and take us to that GitHub repository. I said we were going to be looking at Seaborn GitHub, so I'll just Google search it myself. Of course, you can use the link in the chat, and we'll click on the Seaborn GitHub repository. Now, when you first come to this page, you are going to see a huge number of different things that you can click on and different things you can explore. To note, in the main portion of the screen, from here down that I've highlighted, these are all of the files and folders that exist within this GitHub repository. And so if I want to go look at the contents of any particular file, I can click on any file. Or if I want to open up a folder to see what's inside of it, I can click on any folder and it will take me into that folder so I can see all of the files that live within it. Before we talk about all of the files, we're going to talk about those properties that I mentioned. So we're going to talk about some of the properties that kind of mark or show you that this is a healthy project and it gives you confidence that you can or should use it. So the first property that we mentioned we're going to talk about is our GitHub stars. Up here in the top right, just below the main toolbar, you will see that we have three widgets. We have our watches, our forks, and our stars. And if I go right to left, we'll start with our stars. Your stars are most similar to the likes on a social media post. If you have a lot of stars, that means a lot of people have enjoyed using the code in this repository or the tool in this repository so much that they'll come back and they'll leave you a like or a thumbs up, or in this case, a star. 13,000 people all leaving stars is pretty convincing because unlike social media, this is not as popular and as widely used or digested. And so seeing 13,000 stars on a GitHub repository, that is no small feat. So 13.4 thousand people have liked this tool, liked it enough to come back and leave it a star. Additionally, we also have our date of last commit. We'll talk about forks and watches in just a moment. I want to instead guide your attention down here to this toolbar. This particular line right here on the screen, this tells you what was the last change made anywhere in this repository, who made it, and when was it. So I can see that this individual made a change, and the message they incorporated with that change is to fix a small typo, and they did this about 1 month ago. And so in the grand scheme of things, having something being updated about every month, that's a pretty good cadence, especially in the world of open source, where this tool is nobody's being paid to maintain or work on this tool. It is a passion project. And support, it's honestly a foothold for a lot of statistical data visualization. We can click on this particular button here and we can see the entire what we call commit history. Remember earlier I said that commits are just snapshots. And so this is what the snapshot of all of the files and folders in this repository, what they all look like after the small typo is fixed. This snapshot down here, this commit down here, well, that's what all of the files and folders in this repository looks like before that typo was fixed, but after the mock array interface was fixed, whatever that might mean, and so on and so forth. And you can see when these things were made. So July 10th, January 26th, there's a fairly large gap in there, but before January 26th, it looks like we had a small burst of work about a month apart. So this gives us some confidence. We can kind of see that the cadence that this thing is updated at, it's being updated not every day, not even every month, but maybe once every other month on average. And that's pretty good in the world of open source tools. But let's come back to the main GitHub repository. Earlier, I took our attention away from the forks and watches, so let's zoom back in on that now. Fork effectively means that you are going to create a copy of this same repository in its current state under your own GitHub profile. And the reason we do this is because I do not own this GitHub repository. I told you that Michael Wascom owns this GitHub repository. Michael Wascom is the individual who created this tool. This tool lives under his profile. And to avoid any conflicts of maybe interest or just conflicts of workflow, you cannot go to Michael Wascom, the official repository of Seaborn, and make changes. I can't open up any of these files and simply make a change and save that and have that be the state of truth. It's not a Wikipedia page. And so what we have to do is we will typically fork or copy this repository to our own profile. We make those edits on the copy of under our own profile. And then when we have finished making all of our edits, we then compare our copy to the current copy that Michael Wascom has. And we say, hey, Michael, do you want to integrate the changes that I have made in my own copy? You can see them all right here. This process that we have just outlined is what we call a pull request. Effectively, with a pull request, you're saying, oh, I've noticed maybe a bug, or maybe I encountered an issue and I know exactly how to fix it, or maybe I saw a typo in the documentation. And so what you would do is you make a copy of the whole repository, you fix that typo, and then you open up a pull request comparing your copy to the current official copy. And so here you can see all of the open pull requests. Meaning these are all of the changes that have not yet been incorporated into the main version of this tool. And so what we're looking for inside of a healthy repository is, one, the fact that there are pull requests being created, but two, we're also looking for feedback here from the maintainer or some type of involvement from Michael Wascom, since he is I believe, the sole maintainer of this tool. And he's going to say, oh, this looks like a good change. We'll go ahead and incorporate this. Or can you also make this change and that change? And so pull requests are a great place to make changes. Next to our pull requests, you'll also see the issues, and these are along the top navigation bar here. The issues for this particular tool, what we're typically looking for here are more closed or solved issues than there are open, which is always a good thing. And we are also checking to see how recently were these issues opened, or do we have some really, really old issues kind of lingering about? I will say having old issues lingering is not the worst thing to ever see, but what we should be probably seeing is some type of correspondence between the maintainer as well as the individual creating the issue. And so this is a great issue. This person is saying that the line plot does not work when hue changes along some specified units. And what they've provided here is a minimal reproducible example, or what they call an MWE, also called an MRE. MWE is a minimal workable example. MRE is a minimal reproducible example. It just means that you should be able to copy and paste this code exactly as is, and it will run on your computer, provided you have the package installed appropriately. And so they are claiming that there's an issue inside of the output here. What I wish this individual did was include a snapshot of the resultant image, and maybe some arrows saying this looks wrong to me or that looks wrong to me. But issues are not there to tell you that you should never use this project. Issues are actually here to say that people are actively using this. It's actively being identified for any problems that arise, and then those issues are actively being addressed via the pull request mechanism. And so that is our stars, our commits, our commit history here, our pull requests, and our issues, as well as our forks. The last thing to talk about in terms of properties of a GitHub repository are our watches. I wouldn't say watches are too important, and I wouldn't weight a lot of things on a specific number of watches. All watches mean is that there are 255 individuals who want to be notified with every single change that is made to this repository here. Not horribly interesting. I wouldn't tell you that you should be watching any GitHub repository unless you're actively working on that repository. But if you're not, the watches aren't too important. So those are our important properties, and it's also kind of a tour of the GitHub interface. On the other hand, we also have paraphernalia, meaning files more often than not. Our paraphernalia come in the form of documentation, legalities, collaboration, credit, and history. And there's going to be a specific file within each repository that should be present. If any of these files are missing, this is when I would start to raise a little red flag of, wait a minute, is this actively worked on? If there's no license, I can't use the project. If there's no contributing guidelines, well, maybe I'll just open up a pull request and hope for the best. If there is no documentation, I don't even know how to use the thing. So these are all important to have as well. So let's take a look back here. The first thing that we highlighted was documentation, a README file. And if you scroll down here, we can see that there is, in fact, a README file. These are often kept at the base of the repository, just meaning that I shouldn't have to open up a folder to then find a README. In fact, even GitHub thinks that this is an incredibly important file. I'll click on this particular file. You can see that it is a .md. It's a markdown file. And so it is very nicely rendered. And so you can see they use that inline rendering trick with the exclamation mark and the square brackets to get this image or the logo here. And we have a bunch of other information. I'll step through this information, but I did also want to point out that you don't have to actually click on the README to see its contents because GitHub knows and understands that the README file is very important. And in fact, it will automatically render it just at the bottom of the repository for you. So you can see that we have the README here, the logo, a title, which is a great thing. We have a description. What does this thing do? We have links to documentation. How do you use this thing? What are some examples of using this tool? We have declared dependencies, though I would probably rely on the requirements or the environments or the Pixie TOML file, whatever tool you're using to declare dependencies, and not really rely on the written format because these can come out of date. It gives us copy and pastable commands that we can use to install this tool. So if I want to try using Seaborn, well, I can pip install it or I can conda install it. It also gives you guidance on how to cite this tool, because this is a tool that has been published in JOSS, or the Journal of Open Source Software. And if you're going to be contributing back to this tool, it tells you how you can run the tests and it tells you how you can do development. And with that said, that is our README. It provides a lot of important metadata that are just human readable. And oftentimes it will give you commands that you can copy and paste or examples that you can run. In this case, it links us out to particular documentation. So besides the README, we also have a license, and this is the legalities here. The license is going to tell you what you can and cannot do with this repository. Typically, the open source licenses, or the license that you'll see assigned to open source projects, are going to be fairly open, meaning that you can use or reuse the code or whatever you find in this GitHub repository with or without some modification, and you can do almost anything that you want. And what most of these open source licenses will waive is liability. If this code has a bug in it that the author is unaware of, you cannot legally come after them. You cannot sue them. You cannot pursue any legal action. You just have to say, it's a bug, let's go and try and fix it. And so that's typically what these open source licenses will do. They'll also have maybe some stipulations about citing them if you use this particular code. So make sure that for any license, you read through the text. I promise you the text is not as dense or confusing as other legal documents I have seen. And I'm going to be showing us a couple of resources today as well as tomorrow about where you can find maybe some more human or regular or people-friendly versions of these licenses to figure out what they are all implicating or implying. But having a license is incredibly important because if there is no license, you cannot use the tool. You have to assume that it is strictly copyrighted. We'll also see down here some contributing guidelines. If you want to get involved with a project, if you want to open a pull request, well, here is how you go about doing that. If you want to report a bug, the author asks that you follow these guidances or guidelines. If you want to contribute or pitch a new feature, well, you should open up an issue to discuss the feature first before you go put in a lot of work. Finally, we also have our credits. Now, earlier in the README, I said that there are some guidances for citing a paper, but we'll also see that if we come up into the files here, there's a license.md. This has that BSD3 clause license that we just saw. And we also have a citation.cff. And the citation.cff file has all of the metadata that you are going to need to actually cite this repository. So this uses the preferred citation tag here, and it will tell you that it's an article that's been published, who the authors are, what their ORCID is, what the DOI is. So if I do want to resolve this DOI, I can go to doi.org and I can find this paper. And if you've never done that, this is always a fun activity to do. A DOI is just a permanent link or a permanent space on the internet that will house some digital artifact. And when I say permanent, of course, it's permanent with an asterisk, but the guidance here for DOIs or digital object identifiers is to be as permanent as possible. And so what I'll do is I'll go to doi.org, and then you scroll all the way down to the bottom, and then you can paste in that DOI that we just grabbed from Michael Wascom's repository, and we simply click Submit. When you do that, it will take you immediately to the publication or to whatever digital object is being referred to by that DOI. You can think of a DOI as almost like a URL, like a google.com/ or maybe like my blog or my homepage.com/blog. This is similar to a DOI, except it is resistant to changes in the underlying website, meaning that just because I have a website at myhomepage.com/blog today, what happens if I decide to delete the blog tomorrow? Then it's gone forever. You're going to go to this website and you're going to see a 404 page not found error. DOIs are designed to never 404 on you because they have strict guidances on what to do if they do need to change the underlying URL or the location of the digital object and keep that same DOI always pointing towards that specific version of that object. Of course, if going to doi.org and then scrolling to the bottom and then pasting in a DOI is too much, I understand. And so what you can also do is you can go to doi.org/ and then just paste in the particular DOI that you have. And this will also automatically take you back to the underlying publication or whatever digital object that DOI points to. And so that is all of the metadata that you'll find inside of a citation.cff. Redundantly, .cff stands for citation file format. So this file name literally reads as citation.citation file format, which is always a funny thing to encounter. Last but certainly not least, earlier I walked us through the commit history. And what I would never do is actually read through this commit history. The changes are too small and too fine-grained. Unless I'm looking for something incredibly specific, we will not be interested in the fact that you made a small typo change or the fact that you fixed the mock array interface or the fact that you support array-like masks in heat maps. What we will likely care about is what are the high-level changes, the large changes that come out every couple of months or so that I really should care about. Now, for some places, you might need to dig around for these, but typically it's going to be under something typically called release notes or human readable history. And so from here, you can see what's been new in each version. The last minor release was about a year ago, and this was part of ongoing work to improve what Michael Wascom coined as the object interface. If you're familiar with ggplot2 and R, it's a more similar interface to writing code in that style, following the grammar of graphics closely, but not perfectly. And you can see here are all the changes that have been released over time, as well as all of the information related to them. And so that's our human readable history. And that takes us to the end of our paraphernalia. We know that we have documentation, we have legalities, collaboration, credit, and history, and we know where to find them on GitHub. And if they are not present, that starts bringing questions of, well, should I use this tool? It's not very well documented. Or it can tell you that, wow, this thing's very well documented. It has the appropriate license. It has collaboration guidelines. So clearly they're used to working with other people. It's been published, so on and so forth. Now, let's take a moment to link back to one of our guiding acronyms that we saw earlier. We had our FAIR acronym. I told you that FAIR applies to pretty much everything that we'll do or talk about in open science. And what we just talked about are metadata. If we look back at these, you'll notice that never in a single one of these files or a single one of these navigation bar widgets did I say, here's the actual code, go read a bunch of Python scripts. And so these are often coined as metadata. They are things that describe the data that lies therein. And so our FAIR acronym supports our metadata because if you have a metadata source like our citation.cff file for giving credit, well, GitHub actually searches or indexes the citation.cff file to help you make your results or help you make your repository more findable. You also have the fact that it's on a GitHub repository. It is publicly posted and it is freely accessible. This helps the accessibility of our project. We have collaboration guidelines. This helps us be interoperable because we are advocating to working with other people. And of course, the documentation will also help here as well. Having a history or the change log also helps interoperability because it helps rationalizes what decisions or changes were made and why. We have the documentation. As I said earlier, it helps with interoperability because it gives examples on how other people can start using this thing, and it helps with code reuse or reusability. And finally, we have our license for our legalities. This helps with reusability because remember, without a license, you actually can't use the thing that you just found. And so this goes to show that our metadata sources all support our FAIR acronym. Now, this is a small page. If you're working on software tools, check out the documentation diataxis, but I suspect many of us are not working on documentation tools, or working on software tools, so I will be fairly brief with this slide. Documentation diataxis is a thought process for how one should organize documentation for a given tool. So if you're looking to write better documentation, I would highly recommend that you check out diataxis.fr. The idea is that you want to split your documentation across two axes, a dimension that specifies action versus cognition, and another dimension that emphasizes acquisition or understanding versus application. And so if you focus your documentation fairly evenly across creating tutorials, across creating how-to guides, across explanation, and across reference, well, then you're going to be pleasing most of your target audience. Typically, if you have an audience that's new to a tool, they're going to lean more towards the tutorials. If you have an audience that's very familiar with the tool, well, they're just really going to be reaching for the reference information at that point. So making sure that you split your efforts is always a good thing for writing documentation. We also have the license. Now, we talked about the license, but I did just want to re-highlight to you that a license tells you what you can, permissions, and limitations, what you cannot do. So for your permissions, yes, you can use this tool for commercial use. You can modify the source contents. You can redistribute it as you see fit. You can even use it for private use. The limitations are liability and warranty. Liability meaning if something goes wrong, the author is not held liable for whatever went wrong or whatever resulted from it going wrong. And the warranty says that because you found a bug, the author is not necessarily under any obligation to then fix that bug. So they will fix it out of the kindness of their heart when they find time in their busy life. And this is what you'll typically see in most open source licenses. Now, there are other types of licenses, and typically we will differentiate our licenses that we use for code from our licenses that we use for other materials like papers or data sets. And typically, what you will see in this dichotomy is that the code licenses will always have something to say about the source code and whether they can be modified or redistributed, whereas the data or article licenses will typically be more about copyright and citing an appropriate citation or using for corporate use. And so in this case, I would highly recommend, we're going to be talking more about the non-code licenses tomorrow, but I cannot highly recommend enough. My colleague Lorena Barba's licensing reader created as part of George Washington's open source project office group. So check out that link if you want to learn more about all of the different types of licenses. There is a wealth of information in there that we won't be going to as in depth. Remember what I said earlier, a license is simply a contract that tells you what you can and cannot do. If there is no license on a particular repository, you cannot use the contents of said repositories. That's really the bullet point summary. We don't need to go through all of these points here. Now, an important thing to note is that licenses do exist on a spectrum. And so typically, we will see licenses that are more open or public domain, and you'll see licenses that are more closed or proprietary. Our open licenses, the public domain simply means that anyone can do absolutely anything that they want to use it. They don't need to cite you. They don't even need to involve you or let you know. On the other hand, our proprietary licenses mean that you cannot copy change, redistribute, even use the tool unless you have access to the license. And typically what's going to happen is that you have to pay some entity continuously for continued access to a particular tool. A great example of this is the MATLAB programming language. If you want to be able to use MATLAB, you have to pay MathWorks, the company, for their license. Typically, if you work at a university, you'll have access to fairly cheap licenses. Maybe your lab already has a group license that you can use. This makes it convenient. But I will say, if you do not work at an academic institution or an institution that has a license, the non-academic individual licenses for this tool are incredibly expensive. And that makes your work not reproducible for those particular users. Of course, you can always shift to an open source alternative, something like Octave, which will help you write MATLAB code or MATLAB-like code without the backing of MathWorks and, of course, without the proprietary license. And I will say, typically for our projects, our works, for them to be public, reusable, we will want to gear ourselves towards the lesser general domain or the permissive licenses. Now, how do you go about choosing a particular license? Well, this is a fantastic question. And for this question, what we want to focus on is simplicity. We'll talk about code licenses here. How do you choose a code license? Well, the easiest way to get started is to go to choosealicense.com. This is actually a website that's created by GitHub to help code writers, I should say project owners, choose a license for their particular project. It gives you a very easy point and click option where maybe you want to focus on working in a community, or maybe you just want to keep the license simple, just kind of bare bones like the one we saw on with Michael Wascom. Or maybe you care about sharing improvements. Maybe you say that if you make an improvement to this software, you have to incorporate it back. But then you can also choose the option, well, maybe your project isn't software, maybe you just want to explore other licenses, and then the hypothetical of what happens when you don't. The shortcut is that nobody can reuse your stuff legally. So we'll keep it simple and permissive. You can choose the MIT license here. It links you to this exact license. All you would need to do is copy and paste it into a license file inside of your repository, and there you go, you have a license. If you want to work in a community, it's going to give you a couple of more options, and there's going to be a couple of more restrictions here. And so typically, if you are looking to add a license to an existing project or community, it gives you some guidance on other programs or other tools that already have licenses, and you can see what they do and why they do it. So it just gives you an easy way to explore some of the license options that exist. I will say that reader that I shared with you from my colleague at George Washington, Lorena Barba, that gives you, honestly, a deeper wealth of information than the choosealicense.com. Really, this is just an easy way to point, click, select a license, and you're done. When talking about collaborating, if you're working collaboratively on software, you should absolutely write a guide for how you want to interact with people. Otherwise, you're going to get a bunch of collaboration in formats that you didn't want. Maybe they're making wide sweeping changes and they didn't run it by you first. And so this will typically help us avoid that specific scenario. Of course, we have our citation.cff file that we talked about. It's a plain text file. If you are privy to other file types, this is really just a YAML file, but you can see it gives you all of the information you would need in order to cite this particular resource. This gets us into a little bit of the contributor role taxonomy because the citation file format supports the contributor roles, meaning that if you have, let's say, an article that you published, and that article has 50 authors, well, I know that not every single author wrote 3 to 4 sentences of text and then they glued it together. They didn't do that 50 times. What likely happened is that the first, second, and third, the first author wrote the rough draft of the paper. The first, second, and third author went back and forth on some major revisions. And then the 5th through 49th author is typically going to have been involved. Maybe they were part of like the data collection, or maybe they actually made edits to the paper, or maybe they helped out with some code, or maybe they helped out with data visualizations. And then the 50th author is likely the overseeing author, the PI, or some supervisor in this capacity. And what's very important is when you do have papers with 1, 2, 3, or 50 authors, it's important to identify what they all actually did. And so the contributor role taxonomy helps disambiguate what every single contributing author did. Were they involved in conceptualization? Were they involved in the software or supervision or visualization, so on and so forth? And that is what the credit contributor role taxonomy gives to us. It's a format that lets us actually mention what each person actually contributed here. You can read more on the credit.niso.org page. There are more and more journals that are supporting the contributor role taxonomy, so I highly suggest you incorporate that out of the spirit of transparency and openness. And of course, we want to ideally avoid the occasion when there are 50 authors and 10 of those authors made 0 contributions. They just wanted their name on another publication, and somebody had enough sway or somebody was nice enough to allow them to do that and attach their names to a project that they made no intellectual contributions to. So that is the purpose of the contributor role taxonomy here. We talked about the history changelog, how the commit history is just too fine-grained. People typically don't read through this. Instead, you want to look at a changelog or some type of release notes to provide a human readable interface for all of the changes that we have here.